this video, we're going to combine together, these lessons are going to combine together topics 6.6, 6.4, and 6.7, all dealing with the fundamental theorem and applying properties of definite integrals. So how to use the fundamental theorem of calculus to find the area under the curve is our essential question. And then we have a lot of I can statements, so take a minute, pause the video, get them all written down. I can find the area under the curve given a graph. I can use properties of definite integrals. I can calculate a definite integral using areas. I can integrate an exponential function. I can integrate 1 over x. I can use the fundamental theorem of calculus, abbreviated FTC, to integrate a definite integral. And extension 1, I can use the FTC to integrate the short method when the chain rule is present. All right, so the fundamental theorem, this is like the huge thing. This is must, because it says fundamental, this is what calculus is about, right? Other than slope, right? So if f is continuous on a to b, and this is a bracket, the closed interval a to b, and differentiable on the open interval a to b, then the integral from a to b of f of x dx equals, and remember when we use a capital F, that means antiderivative, f of b minus f of a, where f of x is the antiderivative of f of x. And remember, integral and antiderivative are kind of interchangeable words. So what we are supposed to do here, oh, great. It did all kinds of craziness. Okay, so I'm sorry that mine did that. Hopefully yours isn't like that too. In the next few examples, consider the function f of x equals negative 2x, whose graph is pictured below. Calculate each of the following definite integrals according to the fundamental theorem of calculus. Then shade the area of the region that the integral represents. So let's actually, I'm going to start with the shading and calculate my area with the shaded area, and then we will go to then we'll do the integral. So it says here in the integral that we're evaluating from negative 2 to 1. So I'm going to go to negative 2 here to 1, which would have been here. So it looks like the shape that I just got was a trapezoid. So let's really quickly calculate the area of that trapezoid. So I know it's a trapezoid, starts with the t, we divide by 2. The base, one of the bases looks like, if I come from this length is 7, and then this length here is just 1, and then the height is in between here is 3, it looks like. So let's see, I have 7 plus 1 is 8. 2 goes into 8 4 times, so it looks like my area is 12. So let's see what happens when we actually calculate the area using the definite integral. So I'm going to integrate what I've got, which means, remember, we add 1 to the exponent. So we've got negative 2x squared divided by my new exponent 2 plus 3x. And then instead of writing a plus c, we're going to write this bar, okay, which is just notation for meaning, hey, we got to still plug in these bounds. I'm going to cancel here. So we've really got negative x plus 3x from negative 2 to 1. So I'm going to substitute in here. So I'm going to plug my 1 into those first. We always use the number that's on the top first. So it's negative 1 squared plus 3 times 1 minus, and then always a big parentheses, negative 2 squared plus 3 times negative 2. All right, and we got to be careful because that negative is on the outside of the squared. So we'd have 1 or negative 1 plus 3 minus parentheses. Negative 2 squared is 4, but it's still negative out front. And then 3 times 2 is negative 6. And then let's see, we've got 2 minus negative 10, which is in fact going to be 12, which matches what we got before. So yay, they match. So you can now see that the area that we calculated with the trapezoid is exactly the same as when we integrate. So you can see that the integral calculates the area under the curve. All right, so I'm going to use my shading, do my shading first. So we're going to go from 2 to 5 this time. So 2 to 5 would be what would get shaded this time. I already know that it integrates to this guy right here, so I'm just going to go right there. So negative x squared plus 3x. But this time I know I'm plugging in from 2 to 5. So let's see, negative 2 squared plus, sorry, I got to do the 5 first, whatever's on the top first. Negative 5 squared plus 3 times 5 minus, big parentheses, negative 2 squared plus 3 times 2. So we have negative 25 plus 15 minus parentheses, negative 4 plus 6. Again, that negative is outside the squared. It's like saying negative 1 times 2. All right, so let's see, when we calculate this, I'm seeing negative 10 minus 2, which would be negative 12. Interesting that the area is negative this time. Let's see if we can do one more of these. This one here, it looks like I'm going from negative 1 to positive 4. And notice there's a little bit above and a little bit below the axis this time. So I still know that when I integrate this, that I have negative x squared plus 3x, and it's going from negative 1 to 4. So we're going to go ahead and plug in. So I've got negative 4 squared plus 3 times 4 minus parentheses negative 1 squared plus 3 times negative 1. So 4 squared would end up being negative 16 plus 12 minus, that negative 1 squared is going to go positive, and this is negative minus 3. So we've got minus 4 minus negative 4. Double negative goes positive, and my answer is 0. Because notice, look, the triangle above and the triangle below look like the same area, but above it's going to be positive and below it's going to be negative.